After watching this video, you will never see a mouse the same way again. When we click the mouse, a physical switch closes the circuit and sends an electrical signal through the wires. Since mouse is connected to the motherboard, the signal reaches the motherboard controller chip, which then notifies the CPU by raising an interrupt. The CPU immediately switches to the interrupt mode and enters the kernel through the interrupt descriptor table. The kernel's handler finally forwards the event to the application that uses it. Before diving further, we need to understand that a mouse can be attached to the motherboard via two different types of connectors, a USB connector or a PS2 port, not to be confused with a PlayStation. In this video, we'll be looking at the PS2 connector because unlike USB, PS2 uses real hardware interrupts instead of scheduled polling. When we connect a PS2 mouse, the motherboard has small dedicated ICs that talk to the mouse. In PS2 systems, these ICs are known as i8042 controller. To understand the protocol better, we can check its implementation in the Linux kernel. Let's start by searching for i8042. Currently, we see a file named i8042.c inside driver/input/serial.io. Here we see setup AUX, this is for mouse, and we also have setup KBD, which is for the keyboard. Let's keep on exploring the driver code. If we look inside the function's body, we find a request IRQ call. To understand what's happening here, we need a high-level idea of how Linux handles interrupts. We can use the Linux kernel map, which shows different kernel subsystems and how they're linked together. It's a bit outdated, but it's still very helpful. Zooming into the interrupt section, to find request IRQ, we see that it leads to setup IRQ, which creates an entry in the IRQ descriptor table. The IRQ descriptor is used by the generic interrupt handling function. If we backtrack the caller for the handler, we see the CPU's interrupt entry point invoking the handler after the interrupt occurs. In simple terms, request IRQ sets up a callback entry that gets triggered whenever the CPU dispatches a hardware interrupt from the mouse. Going back to the driver code, we see that the driver registers the i8042 interrupt function as the interrupt callback. Exploring the body of i8042 interrupt, we see that it calls i8042 handle data function. Inside this, we can see data field, which is populated using the i8042 read data function. After the data is read, it is passed to the serial.io interrupt function. If we can somehow see the data being sent to the serial.io interrupt, we can actually observe the raw bytes coming from the mouse. For normal binaries, we would use a debugger, but for kernel debugging, what do we use? Fortunately, we can still use GDB, but we need to enable kernel debugging support while building the kernel. So, we're going to build the kernel starting by installing some dependencies required for compilation. Then, we pull the source code of the kernel and we build the kernel with debug flag on. This will take some time. While waiting, we can build our main program that will run as PID1 in the kernel. It can be any small program. In my case, I created init.c, which simply prints some text and waits for the input in a loop. We archive it into a CPIO image. Once both kernel and CPIO are ready, we can boot our kernel using QEMU, which is an open source emulator and virtualizer. We pass the kernel path, the CPIO file, and I also added a no-KASLR flag to disable the address space randomization. Finally, we also pass -s flag to expose a GDB port at 1234. Once we launch the kernel, we will see it booting up. This takes a few seconds, and once completed, it runs the init process that we made. We can fire GDB in a parallel shell and pass vmlinux as the debugging symbol file. Then, GDB will read all the debug symbols. Then we can attach to the QEMU debugging port and set a breakpoint on the serial.io interrupt function we saw earlier. Now we continue execution, and when a mouse event occurs, the breakpoint will trigger. We can either print the data manually or write a small GDB script to print each packet. And then we can press C to continue. Let's perform some actions with the mouse and analyze the output in a structured way. PS2 peripheral devices send the data in a packet of 3 or 4 bytes. 4 byte if the mouse has a scroll wheel, but we'll focus on the basic clicks and motion. If we break down the bytes, we find overflow indicators for X and Y, the sign bit, the button states, and then 1 byte for each X and Y movement. Also note the always 1 bit. It is used for packet alignment. When the mouse is idle, the movement bytes are 0, except the alignment bit. When we click the left button bit becomes 1. Similarly, the right button bit turns on during a right click. After releasing, the mouse sends another packet showing no buttons pressed. If I move the mouse upward, all the buttons remain off, but the Y movement is positive. Moving downward produces a Y delta with the Y sign bit set, meaning negative direction. Similarly, we get X delta when moving right, and negative X delta with the sign bit set when moving left. Notice that the mouse never sends absolute positions. If I move the mouse diagonally in the upward right direction, both X and Y deltas appear. Putting it all together, when the mouse moves or clicks, it sends the data to the I8042 controller on the motherboard, which triggers an interrupt. The CPU has an interrupt descriptor table register, IDTR, which points to the correct interrupt handler entry. The handler saves the CPU states, runs the kernel IRQ dispatcher, which calls do IRQ or its modern equivalent, looks up the handler register, and after dispatching, restores the save state and resumes the normal execution. Interestingly, the kernel never stores the absolute cursor position. The GUI environment is responsible for tracking the pointer and updating it. Now, about modern USB mouse. They don't use true hardware interrupts. Instead, the USB host controller pulls the device at fixed interval using USB interrupt transfer. And finally, PS2 also supports keyboard interrupts. So if you are interested, you can try the same exploration with the keyboard events. Thank you so much for your time. I hope that you learned something new from this video.